In this problem, we're going to look at how to calculate an equilibrium constant and then to determine whether the conditions given are at equilibrium, and if not, which way they are proceeding. So the following reaction occurs in air at ambient conditions. The equation is listed up here. And so the first part of the question asks if the pH equals 6 and the concentration of iron 2 plus is 10 to the negative 10th moles per liter, is the reaction proceeding to the left or the right? And part B, if we are not at equilibrium under the conditions in part A, what pH would result in equilibrium if iron 2 plus is still 10 to the minus 10th moles per liter? So how do we start? Well, we know that in order to determine whether the equation is proceeding to the left or the right, we're going to have to calculate Q, the reaction quotient for the conditions given, compare that to K, the equilibrium constant, and if Q is equal to K, then we are at equilibrium. If Q is not equal to K, then the reaction will proceed either to the right or the left, depending on whether Q is less than K or greater than K. So we're not given a K, so we know that at some point we're going to need to calculate what K is for this reaction. We're also going to need to calculate what Q is for the conditions given. So let's start by writing out our equation for what Q is. So here we are, part A. The equation for Q for this reaction says Q is equal to, and this is going to be the activity of the products raised to their stoichiometric coefficients divided by the activity of the reactants raised to their stoichiometric coefficients. So Q equals the activity of H plus to the fourth times the activity of FeOH 3 solid squared divided by activity of H2O to the fifth times the activity of O2 gas to the 1/2 times the activity of Fe2 plus squared. So now we're going to simplify this using the activity rules we talked about in class. For H plus, this is just a constituent dissolved in water, so the activity is going to be equal to the molar concentration, H plus to the fourth. FeOH3 solid, this is a pure solid. For those, we're going to assume that the activity is 1. On the bottom, H2O is our solvent. We said in those cases we're going to assume the activity of that is also 1. For O2 gas, for gases, we're going to assume the activity is equal to the partial pressure. So for this, we're going to have P sub O2. And then we're going to have Fe2 plus, which is just a concentration again. So we just have H plus to the fourth on the top. Down here, we have partial pressure of oxygen raised to the 1/2 times the Fe2 plus concentration squared. Okay, so that is our Q. Now, we can calculate what the value of this is for the conditions given. We recall that pH equals the negative log of the H plus concentration. Hopefully you learned that in general chemistry. And so if our pH is 6, we can solve for our H plus concentration, which is equal to 1 times 10 to the negative 6th. And then our partial pressure of O2, here we need to know one other piece of information. We're reminded that the problem up here in the original problem statement, this is in air. it turns out that the partial pressure of an individual gas in a mixture of gases is equal to the volume fraction of the individual gas times the total pressure of the mixture. So if this is at ambient conditions, then we can assume that the pressure is about 1 atmosphere. The volume fraction of oxygen in air is 0.21, about 21% of air is oxygen. And so thus we have the partial pressure of O2 equal to 0.21 atmospheres. And then we're given the concentration of Fe2 plus in the problem statement. So we can plug H plus partial pressure of oxygen in air and Fe2 plus into our equation up here for Q, and we can solve and find that Q equals 2.18 times 10 to the negative 6th. So now we have Q. Now we're going to need to calculate what K is in order to compare Q to K. So we can look at what is our recipe for finding K. Well, we are going to write out first our equation here for delta G. So delta G equals delta G naught plus RT times the natural log of Q is our general equation. At equilibrium, delta G equals 0, which equals delta G naught plus RT natural log of K. So in order to calculate K over here, we know what R is and what T are. Those are just constants. So we're going to need to figure out what delta G0 is if we're going to calculate what K is. So let's go to our equation for what delta G0 is. We know that delta G0 is going to equal the sum of what we'll call V sub I delta G0 F sub I products minus summation V sub I delta G0 F sub I reactants. So this V is the stoichiometric coefficients on the products and reactants, and the delta G sub F naught sub I is the free energy of formation of the products and reactants, which we can find from table. So I'm going to scoot this up here, and I'm going to start tabulating my free energy of formation of my products and reactants. I've got Fe2 plus, O2 gas, H2O liquid, FeOH3 solid, and H plus. Here I've got my delta GF, and I'm going to do this in kilocalories per mole. Fe2 plus, I looked that up in a table, and it is negative 20.3. O2 gas is a pure substance, so that's going to have 0. H2O liquid, negative 56.7. FeOH3 solid is negative 166.0. And H plus, simple pure substance, 0. So my delta G0 equals first sum of the products times their stoichiometric coefficients. I have 2 times FeOH 3, so negative 166, plus 4 times my H plus, minus 2 times Fe2 plus 1/2 times the oxygen, which is 0, plus 5 times water, negative 56.7, and that all amounts to negative 7.9 kilocalories per mole. So now that I have that, I can go back up to this equation up here in the upper right. I can plug that in here. R and T are just constants, and I'm going to solve for K, my equilibrium constant. So I have 0 equals negative 7.9 plus R, which in these units we can look up and see it's 1.987 times 10 to the negative third kilocalories per mole Kelvin, times T, where in ambient conditions we're going to assume 20 degrees C or 298 Kelvin, times natural log K. And so now we are going to solve for K and find that K equals 6.23 times 10 to the 5th. So now we have our value of K, we have our value of Q that we calculated earlier. So we can compare those two. We determined that Q was equal to 2.18 times 10 to the negative 6th. That is less than our value of K, which is 6.23 times 10 to the 5th. And so we can look at our rules and see that if Q is less than K, the reaction is proceeding. We know we're not at equilibrium because at equilibrium Q would equal K, so we have to either be moving to the right or to the left. But since Q is less than K, reaction is proceeding to the right towards the products. So that answers our part A. Is the reaction proceeding to the left or the right? And now we can go to part B, which says that if we're not at equilibrium under these conditions, what pH would result in equilibrium if we still have the same concentration of Fe2+. So now we can go back to our equilibrium constant equation. At equilibrium K, we know that is 2.3 times 10 to the 5th, and that is going to equal reaction quotient. K is equal to Q. Q is equal to H plus to the 4th divided by 0.21 partial pressure of oxygen to the 1/2 times 10 to the negative 10th squared. So again, we're trying to calculate what pH would result in equilibrium. pH is the negative log of the H plus concentration. So we have all of this. We can solve for our H plus concentration. If we do that, we have H plus equals 7.31 times 10 to the negative 4th. And so the negative log of the H plus concentration is equal to 3.13, which equals our pH. So for part B, we said, okay, we are at equilibrium. At equilibrium, K equals Q. Let's solve for the H plus concentration and determine pH from that.